आपको वो recitation में मिली है, in which we are going to talk about the laws that are probabilistic in nature, but they are applicable when we have a large number of particles. They are so large that it's not possible, at least for the moment. And I can say into the next few decades, or maybe century, to keep track of each individual particle when we have a lot of particles, like for example, the number of molecules in air in this room, or the positions and velocities of individual stars and galaxies in the whole universe. We have about 100 billion galaxies, and each galaxy on the average has about 100 billion stars. So whatever we are going to say roughly is also applicable to, let's say, a huge number of stars in the universe, and let's say the number of electrons in a small piece of metal, or photons in a burning coal or inside star. So इस तरह की situation जहाँ पे we have a lot of particles, the law of conservation of energy, first law of thermodynamics holds, but that's trivial. The law of conservation of energy holds microscopically and macroscopically, subject to the uncertainty principle, because the small fluctuations can be there. But overall, it's going to hold. The focus today that we are going to discuss is what we call the second law of thermodynamics. And I will state this law later, but that's the goal of explaining. Okay, so आपने इसको A level में FSC में already you are familiar with this thing, which in a simple sense says that when you bring two systems closer together and allow them to interact, and they have two different temperatures initially, after a while they would both be at the same temperature. That the system would tend towards an equilibrium with its surrounding. अगर आप एक cold chalk या hard chalk यहाँ पे रखें, after a while it's going to have the same temperature as the surrounding. So we are going to see its basics, and to do that we have already set the groundwork in our recitation. So let me go back there and revisit a little bit, and then I will define a couple of terms, and then we will state second law of thermodynamics in another language today. Okay, so let's say we have a situation in which we have n total number of particles. So for n particles, जब हमने recitation में we consider a box where particles were two-state particles, that particles can either be on the right or left. Then we found that for each macrostate there are possible number of waves for which we can get the same macrostate. For example, अगर 10 particles हैं, we have one particle on right, there are 10 ways of getting one particle on right, assuming the particles to be distinguishable. But we can also generalize it to give particle energies and positions and velocities, and you can now think in the same way. For example, to give particles, let's say 10 quantas of energy, okay, and we have, let's say, 3 particles only. So there are several ways of giving 10 quantas of energy to 3 particles, right? So we can have, let's say, there's this 1h cut omega, 2h cut omega level, 3h cut omega level. You can put, and let's say we have 4h cut omega energy possible. We can put 2 particles here and the third particle here, right? So we get total of 10 quantas of energy. 4 plus 4 plus 2. Or we can, let's say, this level is allowed as well. We can put 1 particle here, 1 particle here, 1 particle here. So for this macro state of particles having 10 quantas of energy, there are several microstates. Okay, so I'm not going to discuss this thing in detail, but we can bring that idea, we can generalize that thing in the same way that for this two-sided room, this is just one example and when we add more properties, we can have several more microstates for the given macrostate, but the idea is still the same. The counting may change. Okay, so for this two-state system, to have an R particle on the right side, this is the number of possibilities. Let's now define another quantity which will help us in discussing these things, and that is what we call entropy. So entropy is simply defined as a measure of possible number of ways for a given macrostate. So one simplest way of defining it would be, let's say we define S to be equal to W. But since usually when we have large number of particles, आप imagine करेंगे we have a trillion particles, and this is very small number if we think about bigger system. For example, number of molecules in this room, there are too many. There are trillions of trillions of trillions of trillions particles. But if you imagine a trillion, to have one particle on the right side, there are trillion ways. To have two particles on the right side, there are about trillion into trillion square ways, and so on. So since it's a large number, we define entropy to be as the logarithm of this number. When you will study information science, that's also going to be the definition. और मुख्तलिफ sciences में जब entropy define करते हैं, there is a different constant here. When we are dealing with thermodynamics, we use a constant called Boltzmann constant, Kb. This is 10 power minus 23 joules per Kelvin. Forgetting this multiplicative number here. So this is how we define entropy. But instead of definition, whenever the word entropy is uttered, you should simply imagine the number of possible ways for the given macrostate. So we can now state second law of thermodynamics in terms of entropy, and that is that when we have a thermodynamic system, after a while it will reach to a macrostate with a maximum entropy. That is actually a better definition for second law of thermodynamics. और ये हमने देख भी लिया कि ऐसे क्यों होगा. इसके अलावा बाकी जो physical laws हैं, they sort of have no reason. For example, F is equal to ma absolute linear equation, but this law has a sort of a reason behind it, and we know that reason, and that is that for the equilibrium macrostate, there are the highest number of possible microstates. So that's why if you start a system with, let's say, 6 particles and all of them on the left, and you allow this thing that particles can randomly cross from left to right and right to left, so after a while, the maximum probability is for a macrostate with 3 particles on the right and 3 particles on the left. Okay? So similarly, let's say I have 2 systems, 1 and 2. Suppose this has 6 particles and this has 2 particles separately. So, and I connect them, that I allow them to interact, that particles can cross from here to here and from here to here. Which macrostate is the most likely state after a while? The one with 4 here and 4 here. And this is what we call the equilibrium state as well. So the system moves from this non-equilibrium state to this equilibrium state, not because of any force that is driving the system from here to here, but simply because this is the more probabilistic macro state than this one. Or actually, ये तो ज़्यादा probable है, but this is also possible. हो सकता है कुछ state के बाद instead of this, you find the system in this state. But इसकी जो probability है, that is much less than the probability of this macro. So the law should be stated like this. Any thermodynamic system tends towards a state of higher entropy. Spontaneously, that you're not doing something externally to it. And you can even state it more briefly with just 3 words. Entropy tends to increase. So these are different ways of stating the second law of thermodynamics. This for us is just a multiplicative constant for historical people. It's a constant that was introduced by Max Planck when he was working with thermodynamics of black bodies, which connects the average temperature to the energies of the molecules. So average kinetic energy of molecules at a temperature T is 3/2 kBT. So it's just a multiplicative constant. So this is the number of ways, okay? So the entropy, if you define it just like this is good enough. However, since we usually deal with particles of the order of 10 power 23 thermodynamics, so historically people have added this word in this definition. But all math, everything will work fine even without this. Isliye, when you go to, let's say, information theory, you actually have another multiplicative constant over here. Because there we work with different systems. For example, if you have an 8-bit system, maybe you can have a number weighted proportional to 8 and so on, or 2 power 8, something like that. So the important thing is just this logarithm. So let's try to see W is the number of ways for a macrostate. A macrostate, did you miss the definition? Okay. So let me just repeat it concisely. But I think you get the idea of macrostate only if you work through it, as we did in the estimation. So let's say you have these 6 particles, and all of them are distinguishable. So there is only one way of getting them onto the left side, and this is a macrostate, and there is only one microstate. But to have one particle on the right side, there are 6 ways of getting one particle on the right side. We can have either 2 or 1 or 4 or 5 or 6. So it means W is equal to 6 for this. So this is a microstate. So for a 2-state system, to compute W, we have this formula that we worked out. So let's say we have total number of particles n. So n are on the right and n minus n are so like. So this is for a 2-state. If you have a system where there are 3 states possible, for example, when I was talking about energy, and particle can either be in state 1 or 2 or 3, then we have 3 factorial for 3 states, and I'll discuss it in detail in the next chapter. So today we are just going to focus on a 2-state system. Okay, so it means that if we define it, and there's another benefit of defining entropy like this. For example, we have a system with in a state which have WA number of ways, and we have another system in a state which can be rearranged in WB ways. So the entropy of this system is log WA, and entropy of this system is log WB. If I bring these systems closer, that let's say they can now interact, what are the number of possible states of this combined system? WA into WB. क्यों? क्योंकि इसकी एक स्टेट के लिए there are WB states of this thing. इसकी दूसरी स्टेट के लिए there are WB. So there are total of WA into WB states. And what's the entropy of the combined system? this is KB log of this क्या हो जाएगा sum log this A AB log WB. So क्योंकि जब दोनों systems they can interact with each other, then we have a combined system. So I'm finding the entropy of the combined system. So we can see from here that the entropy of a combined system is just the sum of the entropies of the two systems happening. क्योंकि मल्टीप्लाई कर रही है टोटल स्टेट्स फाइंड करने के लिए. नहीं, फर्स्ट करें यहाँ पे कुछ पार्टिकल्स दे कैन बी अरेंज्ड इन WA ways और यहाँ पे हैं दे कैन बी अरेंज्ड इन WB. तो अगर हम इनको कंबाइन कर दें so what are the number of ways that all the particles can be arranged in combined fashion? So you can work it out कि इसकी एक स्टेट के लिए there are WB states for this. फिर इसकी दूसरी स्टेट के लिए there are again WB. So there are total of WA into WB states for the combined system. And the entropy of the combined system is now the sum of the entropies of the two. So because of log, in the definition, we have now this additional benefit that when we have to find entropy of a combined system, all we need to do is just add the entropies of the constituent system. There is another consequence of this definition, and that is the, let's say we have a system which starts from an initial state and evolves to another final state. और आप imagine करना चाहें तो उसी two-sided room को imagine कर लें. Suppose we start the system in such a way that there are 9 particles here and 2 particles here, and after a while it reaches a macrostate of 4 particles here and the rest here. So this is some final state. So this has some WI ways of arrangement, and this has some WF ways of arranging this macrostate. So what's the change in entropy from here to there? We can find this change in entropy from final to initial state as KB log WF, KB log WI. So we can take KB common. So ये जो log WF minus log WI है, this is simply log WF over log WI. We can delete this bracket. So this is the change in entropy of a system when it goes from one state to another state. So first करें कि when you begin you have 1, 2, 3, 4, 5, 6, 7 particles on left and 2 particles on the right. And after a while, suppose the system is in a state where 4 particles are on the left and 5 on the right. Okay? So there is some entropy associated with the system here. Okay? And there is some entropy associated with the system here. No, entropy is not a constant. Entropy is defined for each macrostate. So for each macrostate there is different entropy. जैसे भी लिया है, but to get a W है ना, तो हर macrostate का एक W है. Every macrostate has a W. So it means every macrostate has a different entropy. So when a system goes from this state to this state, its entropy changes. And we can compute it like this: final entropy minus initial entropy. So it's this minus this. So it's just the ratio of number of ways of the final arrangement divided by the number of ways of initial arrangement. So this way we can compute the change in entropy. Now from here we can see one thing very easily, that when a system starts from a least likely state to a more likely state and evolves to a more likely state, its entropy increases. And so in the final state, W is greater than the initial state, so this number is greater than 1, so log is positive. Whenever we have a greater than 1 number, logarithm is positive. Whenever we have a number smaller than 1, logarithm is negative. So this is greater than 1 number, this is positive, so the change in entropy is positive. And that's what second law of thermodynamics says, that when you start a system and leave it, it will go to a macro state where entropy is higher than the initial state. Or at least it will remain in it. If you start with a state which is already most likely, you will end up with a state which is still more likely. The same macro state. इसमें 1 2 3 4 5 6 7 7 लेफ्ट में 2 राइट है, इसमें 4 लेफ्ट और 5 राइट. इसकी microstates, you can find that how many microstates are going to be. It's independent of temperature. So this is what's going to happen. And when we have this hypothetical two-sided room, it's always going to be independent of temperature anyway. We assume that particle can randomly go from here to here. So let's see the effect of temperature if we have brought it up. That suppose we have a system in which let's begin actually with two systems. Suppose we have a system and then we have another system, and let's allow them to interact. So this is, let's say, at a temperature T1, this is at temperature T2. So this one has some entropy S1, this has some entropy S2 when they were separate. Okay. So when they are separate, they have this situation and they have some energy E1, total energy E1. Let's say this has some total energy E2. And as soon as they started interacting, and suppose that T1 is greater than T2, so what's the change in entropy? When this one was separate, it was S1. When this one was separate, this was S2. So let's compute the change in entropy of this whole system. So the change is the total change, the change in 1 plus the change in 2. So ds1 is the change in entropy of this one, and ds2 is the change in entropy of this system. And if you assume that volume of both system is constant and number of particles is also constant, because we can change entropy simply by adding number or reducing number as well. अगर ये जैसे रूम है इसके अंदर जो मॉलिक्यूल्स हैं, अगर आप कुछ निकाल लें तो सिस्टम की एंट्रोपी कम हो जाएगी. क्यों? क्योंकि you have smaller number of ways of arranging the system. If you add particle, you can increase entropy. Or if you increase volume, you actually increase entropy, because then you can arrange particle here, you can then put some particle there. So when you increase volume, entropy increases. So let's assume that volume is constant and number of particles are also constant, but we only allow the energy to change. क्योंकि interact कर रहे हैं, let's say इधर से कुछ energy इधर और इधर से कुछ energy इधर and so. So in that case, this change in entropy of system 1 is simply dE1, and the change here is simply dE2, because I have kept everything else constant. I'm coming to the definition of temperature. So this is the total change in entropy of system 1. This is change in entropy of system 2. अब अगर system 1 पे आप concentrate करें, तो उसकी जो entropy है depends in general on volume, number of particles and energy. लेकिन अगर मैं volume और number of particles constant करूं, suppose, then its entropy only depend on energy. So it means that we can find this change in ds1 by finding the rate of change of s1 to e1 and multiplying by the dE, which is the change in energy, and similarly further. But for here, we can see that dE1 must be equal to dE2, क्योंकि जितनी एनर्जी इधर उधर जा रही है उसका नेगेटिव उधर उधर जा रही है। तो दो ही सिस्टम है ना, ये है ये है, तो DE1 शुड बी इक्वल टू DE2। अगर एनर्जी इधर से इधर जा रही है तो वही है जो इधर से कम हो रही है उधर बढ़ रही है, कहीं और से नहीं आ रही। वी आर अज्यूमिंग दैट नथिंग एल्स इज प्रेजेंट। तो इन दिस केस दिस DS टोटल इज, यहाँ पे DE2 रख दे माइनस DE2, तो ये माइनस हो जाएगा। इसको मैं पहले लिख लेता हूँ, पार्शियल S2 पार्शियल E2 पार्शियल S1 पार्शियल E1 इनटू DE2, या वैसे इसको DE ही कह दें। दिस इज सम D। ये फॉर्मूला समझिए यार, कोई भी जो चीज होती है ना जिसमें आपने चेंज फाइंड करनी है, तो यू मल्टीप्लाई द रेट ऑफ चेंज विद समथिंग एल्स। फॉर एग्जांपल dy इज इक्वल टू पार्शियल y पे पार्शियल x इनटू dx, और अगर वो वेरिएबल एक से ज्यादा पे डिपेंड करता है देन यू कीप एडिंग अदर वेरिएबल्स। जस्ट लाइक अगर आप लैब 1 कर रहे हैं, यू ऐड अनसर्टेनिटीज other things. So it's function of E1, so its change is rate of change with respect to E1 and change in E. इसे मल्टीप्लाई क्यों करते हैं? चलिए इस तरह से करते हैं। फर्स्ट करें, अब मैं सिंपल एग्जांपल लेते हैं। हमने ये कंप्यूट करना है कि घर के अंदर जो नंबर ऑफ एप्पल्स हैं उनमें टोटल चेंज कितनी है कल से लेकर आज तक विद रिस्पेक्ट टू द मनी। कुछ पैसे कम या ज्यादा हो, तो व्हाट वी नीड टू फाइंड, वी नीड टू फाइंड द रेट ऑफ एप्पल्स in rupees and then multiply that rate with the number of rupees that are spent. अगर 10 रुपए किलो एप्पल्स हो, ठीक है, तो अगर आपकी जेब में से 20 रुपए कम हुए हो तो कितने एप्पल्स आपको मिले होंगे? 2 kg। तो आपने क्या किया, रेट को मनी से मल्टीप्लाई कर दिया ना। फॉलो दिस और नॉट? यार इतना सिंपल, ये मेरी 2 साल की बेटी भी कर सकती है, ठीक है, सॉरी 2 साल की दूसरी क्लास वाली। तो देखें कि आपने लेट्स से अगर आपने वो दूसरी क्लास की बेटी पे शिफ्ट करना तो आइसक्रीम में शिफ्ट करना, यू गेट 10 आइसक्रीम फॉर 25 रुपीज एंड इफ यू लूज 50 रुपीज, हाउ मेनी आइसक्रीम डू यू गेट? जी आपने क्या किया, आपका DE जो है, जो चेंज इन मनी है, दैट्स 40 या 40 है ना, 40 रुपीज। इसकी समझ नहीं आ रही, ठीक है, नहीं पहले तो इस पे देख, इफ यू हैव सम फंक्शन of x and you want to find its change, it's partial y by partial x into dx. अब y जो है वो आइसक्रीम है, x जो है वो रुपीस है, so you multiply the rate with the total money or the change in money and you get the change in ice cream. या आपको जानबूझ के कहते हैं या वाकई इस चीज का नहीं पता चलता? शुक्र आपका सवाल थोड़ा सा ऊपर लेवल का, ठीक। तो इनका ये है कि एंट्रोपी तो एनर्जी पे डिपेंड नहीं करनी चाहिए, पर इट डज डिपेंड। मैंने शुरू में एग्जांपल ली थी, सपोज यू हैव 10 particles to fill in a quantum well so that the total energy is 5 quanta. 10 particles, 5 मुश्किल होगी, let's say 20 quanta. So this is 1 quanta, this is 2 quantas, h का omega की form. If you have 5 particles and you want the total energy to be 10, you can all put them here, 5 into 2, 10. You can put 1 here and maybe 1 here, then still total is 10. So for the same energy, there are a lot of microstates. And if you change energy, let's say instead of 10, you say the total energy is 20. Then you might have a different number of microstates. So entropy does depend on energy. Okay? Okay, so now let's come to this question. Why the total change in entropy is just the sum? So, जब हम math में, physics में, when we start modeling, and we have 2, 3, 4 systems, and we want to find the change in total quantity, we don't a priori assume that okay, this one is negative or this one is positive if we don't have any information available. We start with the total change is equal to change in 1 plus change in 2 plus change in 3. When we do everything consistently, अगर किसी में कम हो गया तो automatically that number will come out negative. Because we don't know कि किसी की कम भी हो रही है या नहीं हो रही है, कि हो रही है तो किसकी हो रही है. So plus sign on the other hand can always be thought of as minus sign as well. जो result आएगा that will dictate कौन सा positive कौन सा negative. Okay. So I'm sorry, let me just continue a little bit. We'll take more questions later. So we have situation like this, and from here we see that we have this partial S2 by partial E2, and then partial S1 by partial E1 into dE. And we assume that, let's say, if T1 is greater than T2, so energy is flowing from system 1 to system 2. So it means that it's coming from here to here. So if we have, let's say, temperature T1 and current temperature T2, for one single system, we can define now the temperature as a quantity like this, which will make it consistent with this thing as well. For example, this is 1 over T2 and this is 1 over T1. So T1 is higher, so this number is smaller, so that energy is flowing from this one to this one. So this means that if so we actually defined temperature to be partial S by partial E as the inverse of this. So temperature is the tendency of increase in entropy of a given system. So this is defined in terms of entropy to be like this. So with this definition, we can actually, for one system, if we have one system, its ds, a change in entropy, we can define it to be as something. So this is dE by T, and if only energy is interchanging at constant volume, then this dE can also be equated to dQ. So the change in entropy of a system is proportional to the change in is proportional to the heat given to the system. अगर आपके पास एक सिस्टम है, फर्ज करें कंटेनर के अंदर गैस है, you heat it up, जब आप इसको dQ heat देंगे, so its entropy will increase. Entropy will increase simply because you have now required the total energy to be higher. जब higher total energy है, so you can arrange the particles in more ways than previously. And you can start from this thing. First करें, अगर आप classically सोच रहे हैं, the system can have zero energy. All molecules can just come to rest over here. Classically speaking, don't bring the non-zero quantum energy into play right now. So there's only one way of having the system in zero energy, right? That all particles are at the ground state, at the zero energy. If you heat it up a little bit, let's say you give it only 1 quantum of energy, equivalent to 1 photon. और अगर आपके पास 10 power 23 particles हैं, your entropy goes directly to 10 power 23, roughly, of the order of क्यों? क्योंकि अगर आपके पास सारे particle पहले यहाँ पे थे, if you give 1 quantum, you can either get this molecule here, or you can get this one here, or you can get this one here. So there are 10 power 23 ways of giving 1 quantum of energy to this system. So it means by giving a little bit of heat, the entropy has increased. So similarly, if you take out heat, the entropy decreases. So entropy is essentially directly proportional to the heat given to the system. at constant temperature, at whatever temperature it is. So with this thing, we can now find another formula for change in entropy of a system. Suppose this system is at an initial state with an entropy Si, and it evolves to a system of a final entropy SF. So what's such? So for the same system, we can compute the change in entropy in a different way. That delta S SF minus Si is just the integral from the initial state to the final state. So this way we can also compute the change in entropy of a system by integrating over this term. I'll do one example to explain this use, but let me put the idea of entropy on a bit solid ground again, because even though it's very simple, but somehow people find it hard to get it. And जो रेसिडेंशन हमने की है वो बहुत आसान थी, उसका मकसद तो यही था कि I hope that you have gotten it, is the difference between macrostate and microstate. For the same system, for different macrostates, there are more than one possible ways of arranging the system, and entropy is simply a measure of number of ways of arranging a system to get the same macrostate. And the second law of thermodynamics simply says that if you start a system in a non-equilibrium state, it will evolve in such a way that its entropy will increase. So symbolically, I can represent it like this. फर्स्ट करें, ये एक configuration space है, जिसमें एक system की जो microstates हैं, I am representing them with number of dots. तो ये ऐसा system है कि ये ऐसी macrostate में है जिसकी सिर्फ 3 possible microstates हैं. ये इनको 3 particles का समझें, ठीक है, कोई भी है. So after a while, this system will evolve into a macrostate with more microstates, and after a while, it will evolve into a system with even more microstates. So that's how the universe behaves. Simply because of sheer number of particles present in many situations. For example, in thermodynamic system, or even at the level of universe, that universe is evolving in such a way that its entropy is increasing. That there are more and more ways of arranging the particles in the universe, the way universe is evolving. So that's why sometimes this is also called the arrow of time. Number of particles fix होने के साथ ही number of system को evolve होने दें, the entropy will increase until it reaches an equilibrium position. First करें, I have a system in which the left side of a room is filled with suppose 10 power 23 particles and right side is empty. Okay? Suppose we begin in a way that I have a box. The left side of the box is filled with a real gas. Okay? With 10 power 23 molecules. The right side is empty, completely empty, vacuum. Okay? If I poke a hole here, what do you think would happen? Particles will start to go there, right? And after a while, it will reach equilibrium. That's our everyday experience, right? And the reason behind, or अगर आप entropy change देखें तो क्या है? When all the particles are on the left and there's no particle on the right, there's only one way of having this thing. And after a while, when we reach a state, suppose that half n particle are here and half n are here. So let's say this is a final state. So the entropy over here is much higher because there are a lot of ways of having half particles on this side and half of the particles on the other side, right? And you will see a simple example in the book where he has computed the change in entropy for going from this state to this state, it's about 0.96 joules per Kelvin. So the entropy does change and it increases when we go from here to here. बिल्कुल सारे का volume constant. So in the case of universes, go a bit more complicated to compute entropy, because you not only have to consider the constant volume, but the dimensions are also changing in a sort of way. And that's also not, on the other hand, completely understood that in what ways it is expanding. Is it expanding that there is a void somehow of space and simply the galaxies are just going into that to fill that void? Or maybe the universe, the space-time exists only until the edges of where the galaxies are right now, and as the galaxies are pushing, they're creating more space and time. So it's not completely worked out yet that what does it really mean. But in a rough way, that's what is happening. लेकिन अगर आप इसको neglect नहीं करते, जो outer region में the galaxies are pushing apart, even inside the universe, the galaxies के अंदर जो stars हैं, और stars के अंदर जो mass है, और जो जैसे हमारी अर्थ है, इसके अंदर जो mass है, is trying to rearrange continuously in a way that's evolving towards a state of higher entropy, unless you put some work to it. It's actually evolving in such a way that its entropy is increasing. Lekin, there's no force behind it. That is simply because that state is more probable. Let me do it again. So इनका क्वेश्चन है कि गर्म करने से एंट्रोपी कैसे बढ़ सकती है? फर्स्ट करें एक क्वांटम वैल्यू. कंपनी के एग्जांपल से और ज्यादा उसको, ठीक है? अगर आप क्वांटम वैल्यू को समझ जाए, you will be able to understand. So you understood that when we have a higher energy, total energy, there are more ways to arrange particles. Quantum, but even this is just a bigger quantum wave, nothing else. When you are putting AC, then you are doing work on it. That's something else. But at the end of the day, it's energy, and you can also find microstates with respect to the position. The particle 1 here and particle 2 here is a different microstate than a particle 1 here and particle 2 here. So if you compute all of that, when you are keeping volume fixed, you are not doing anything with respect to space. You are not doing anything with respect to number of particles. But when you increase energy, there are, let's say you just think in terms of velocity. So there's a possibility of giving this particle a huge velocity and this one slow and get the total energy same, and maybe giving this much velocity and giving this little bit more. So another combination. So there are a lot of combination of velocities for molecules where you get the same total energy. Okay. So I hope that other people also got something from this. So when you add energy to the system, you have more ways of arranging the system. So that's why the entropy is higher. So I was just discussing this arrow of time, that the systems that are evolving in such a way are actually defining time in a sense as well. The other laws of physics, like Newton's law or Schrodinger equation, they don't define time. They tell you what happens when time changes, but they work equally well if you change time in the negative direction. They don't do any harm. You can compute what would happen if this goes in a parabola like this, or it goes like this. The equations, the formalism works the same way. It's only the second law of thermodynamics that tells us that going forward in time has a different consequence than going backward in the time. Because going forward in time, entropy increases. And to decrease entropy, you have to do work. Because when you leave the system as it is and you let it go back in time, the entropy decreases. So second law of thermodynamics is asymmetric in time. So that's why we can say that this law defines time. So let me see if I have something else to say about this before the. Sorry? It's I have left it like this, and it depends on the problem. I'm going to do an example to explain this. Because when you apply work and energy, overall system's entropy increases. हाँ, लेकिन वो एक पार्ट जैसे फर्क ये रूम है ना, अगर आप यहाँ पे हीटर ऑन करें या कुछ भी नहीं करें, its entropy will increase. You put on an AC, its entropy will begin to decrease. Okay? लेकिन जो साथ environment है उसकी entropy और तेज से बढ़ रही है. So overall, the entropy will still increase. पूरी यूनिवर्स with. So let me do a quick example, then I'll take actually more questions. Example will help you actually understand the concept of entropy again, hopefully. So suppose, sorry, I'll take question after this example. So let's say I have a two-sided room with this many particles on the left, and I want to compute the change in entropy when I let this part interact with this. So my initial state is a macro state with only one way of arranging it, all particles on left, and I want to find the entropy change to a state when I have, so this is my initial state, and my final state is that I have half n particle here and half n particle here. This is my final state. And I want to find the change in entropy in going from here to there. Okay, so let's first compute the number of ways of this state. This is simply n of n or n factorial of n factorial and n minus of n factorial. So we have n factorial of n factorial square. Okay, so actually ये assignment ये example करने का मेरा एक ही मकसद है और वो है एक formula introduce करना. It's very common in statistical mechanics. It's called Stirling formula. क्योंकि statistical mechanics में n usually large होता है और हमें हर प्रॉब्लम में ऑलमोस्ट किसी न किसी बहाने से फैक्टोरियल कंप्यूट करना हो. So when n is large, the factorial can be approximated to a very high degree of accuracy, and the accuracy increases when m increases by this expression. So I'm not going to prove it. You can check some maths book that factorial is approximated with this. और अगर आपका m 100 से ज्यादा हो तो ये error 10% से भी कम हो जाती है. When it goes to let's say a million or a billion, then this is almost the same as factorial. So when because it's factorial, तो यहाँ पे आगे अब यहाँ पे 10 power 23 पुट करें और मुझे कोई कैलकुलेटर आके दे जो ये कंप्यूट करे. ठीक है. और imagine the misery of those people 100 years ago who didn't have access to calculators. हाँ. आप बस ये फार्मूला आपको फार्मूला शीट में भी गिवन होगा. You should know that you can use it to approximate factorial whenever m is large. So let's use this here. M is any number. This can be factorial. M factorial is equal to this. नहीं वो फिर भी आसान होता है. दूसरा अगर कंप्यूट ना भी हो तो sometime it can cancel away as well. So for example in this example, this will be 2 pi n n power n half n power half n exponential minus half n and square so we get WF as 2 pi n तो ये स्क्वायर नीचे ले आए तो ये बन जाएगा पाई n हाफ n पावर n माइनस n ये से कैंसिल हो गया और ये जो n वाला पार्ट है ये से कैंसिल हो गया एंड यू आर लेफ्ट विद हाफ पावर n ये हाफ पावर n ये इसकी 2 का पावर n हो जाएगी इसके ऊपर चली जाएगी और ये एक n स्क्वायर रूट n से और एक पाई स्क्वायर रूट पाई से we will get 2 over pi n square root 2 power n. So this is the number of ways that the final state macrostate can be arranged in different microstates. So if I want to compute the change in entropy using that method delta S, so what we will get is something simpler. So instead of doing that, let me do it from the other way, from this equation. So suppose I want to compute delta S by integrating this equation dq by dt और कौन सा वाला ये n पावर n 2 raised power n कौन सा ये 1 over 2 की पावर n है ना तो इधर आ गया 2 की पावर n ये ऊपर चला गया okay so let me know here do little bit to simplify this formula हमें पता है कि for this gas the amount of heat added जब ये गैस इधर से निकलेगी ठीक है इस तरफ को आएगी then there is some energy that is added or extracted from this is equal to the work done and this work done is PdV. I'm recalling your FSC A level knowledge, so pressure into dV. But we also know that for an ideal gas, PV is equal to N kBT. तो यहाँ से अगर मैं P में पुट कर दूँ, तो dQ would be N kBT dV over V. ये V इधर आ जाएगा, तो ये पीक वैल्यू यहाँ पे करें। अब इसको अगर आप यहाँ पे सब्स्टिट्यूट करें, तो you get N kB gets out of the integral I2F dV over V. वो जो ऊपर T है वो T से कैंसिल हो जाएगा and we have this dV by dV. So this is N kB log V from initial to final and this is equal to N kB log VF minus वो उसके ऊपर T है उससे कैंसिल हो जाएगा. So it means यहां से आ जाएगा ये लॉग है तो ये बन जाएगा N kV log V final over V initial. तो फाइनल वॉल्यूम जो है इट्स डबल ऑफ इनिशियल वॉल्यूम ठीक है क्योंकि फाइनल वॉल्यूम गैस दोनों तरफ थी और इनिशियल वॉल्यूम गैस और लेफ्ट साइड पे थी तो दिस इज log 2 so you have change in entropy as N kB log 2. अब मैं n यहाँ पुट नहीं करा पुट कर ले पूरी 10 power 23 और kB B वैल्यू पुट कर ले you get this number जी क्योंकि फाइनल वॉल्यूम डबल है इनिशियल वॉल्यूम का. इनिशियली the gas was on the left half, and finally it's occupying the whole volume. नहीं, लेकिन गैस तो सिर्फ यहाँ पे थी। नहीं, जितने पार्टिकल इस इनिशियल वॉल्यूम के अंदर थे उतने ही पार्टिकल इस फाइनल वॉल्यूम के अंदर। नहीं, वो तो इनिशियल के अंदर हाफ हो गए ना, लेकिन फाइनल वॉल्यूम तो अब दोनों को मिला के है। आप इस तरह से इमेजिन करें, ओके, तो यू कैन इमेजिन इट समथिंग लाइक दिस। ये बैलून है स्क्वायर टाइप, ठीक है, और यू जस्ट मेड इट लाइक दैट। So initial volume is whatever, the final volume is twice of that. So let's do this. क्योंकि WF के बगैर तो कभी भी you can't find the final entropy. हमने निकाल लिया, उसके बगैर क्यों? There are two ways, because entropy is related to temperature as well, and entropy is related to number of states as well. So let's do it from that formula, okay? So that's a good question. So take the delta S from that expression is AB log WF by WI, okay? AB log final WF क्या है? WF is 2 over pi n square root 2 power n, और WI क्या है? It's 1. So let me do this integral. KB log of 2 over pi n plus मुझे पहले कर देते, फिर आपको क्वेश्चन कर। And this goes to 0 as n is large. अब मैं आपको थोड़ा एक्सप्लेन करूँ। अब देखें, ये पहली अप्रोच है, एंड दोनों अप्रोचेस जो है वो इक्विवेलेंट है। यहाँ पे हमने चेंज इन एंट्रोपी फाइंड की है बाय इंटीग्रेटिंग दिस इंटीग्रल। उसमें जो हीट ऐड हो रही है सिस्टम में, वी कंप्यूटेड इट यूजिंग द आइडियल गैस लॉ, दैट द चेंज इन द एडेड हीट इज इक्वल टू द वर्क डन PdV। तो PV को इस्तेमाल करते हुए वो dq निकाला, तो यहाँ पे पुट किया, you got this integral. So dV over V is logarithm of V. So it has to be integrated from initial volume to the final. So we get to this. और क्योंकि final volume initial का double है, we get this expression. Equivalently, if we use the basic definition of entropy, that is KB log WF over WI. So I put this expression for W final from there to here. और अब एक ये टर्म है और एक ये टर्म में दोनों मल्टीप्लाई हो रही है, तो इनका लॉग क्या होगा? ऐड हो जाएगा, ये लॉग और ये लॉग। मैंने कैंसिल नहीं किया, मैं बता दूं, ये n बाहर आ गया। अब ये देखिए, when n is very large, this number is almost 0, ठीक है, because 2 over pi n, right? And you are left with this answer. So this is the same as that. हाँ जी, WF जो है वो हमने कंप्यूट किया है यहां से, क्योंकि राइट साइड पे हाफ n पार्टिकल्स है, तो n चूज हाफ n, ये आ गया, और फिर n फैक्टोरियल करा। वो वाली बात कौन सी? We can maybe discuss later. We have a few minutes to discuss the light second. देखो लाभ पे भी वही लाभ चलता है। एक लाइट ऑन भी रहती है। बेटा
कितना कितना कितना
अभी और क्या नहीं इसका बटन कोई नहीं ये देखिए कॉस्ट टू स्टॉप है ना उसकी कॉपी करते हैं ये उसमें डी भी तो है उससे turned out in this case it's not इसमें वॉल्यूम इंक्रीज हो रहा है ना अगर वॉल्यूम इंक्रीजेस अगर टेम्परेचर भी सेम हो और हर चीज सेम हो इवन देन बिकॉज ऑफ रैंडमनेस हाँ अगर टू साइडेड हो एक या मैं राइट सेट कर दूंगा वॉल्यूम इंक्रीज और टेम्परेचर के सब कम हो क्योंकि जो स्टॉर्स हैं दे रेडिएटिंग एंड डिक्रीजिंग रेट देखो n प्लॉट्स है ना तो बिकॉज ऑफ प्लॉट्स है apologies यार अभी जाएंगे 2 मिनट बैठते मजा आता तो देखिए okay thank you so it will take a few seconds to warm up इसके अंदर बल्ब होता है काफी स्मॉल so it needs some time to come closer to the page is related to the information entropy. So that's something we are not going to words.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts. Why cream spreads in coffee. Why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has a lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed into two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later peak in a configuration in which the energy is maximally spread out. There's a 13% chance that it will return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object will get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy. And again, start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Thank you. So we'll meet next week. Next talk.